Let's say there are n advertisers, A1 through AN. And let's say each advertiser has the same budget B and that B is greater than n. There are going to be n times B queries that appear in n rounds of B queries each. Right? So we're going to actually get one query at a time, but we're going to group them into n rounds of B queries each. And here's how the bidding works. With the queries that come in round 1, the bidders are A1 through AN. For the queries that appear in round 2, the bidders are A2 through AN. For the queries that appear in round I, the bidders are AI through AN, and so on until round N. The queries that appear in round N, the only bidder is AN. And remember, there are B queries in each round, and B is also equal to the budget of each advertiser. So the optimal algorithm in this case is to assign the round I queries to the ith advertiser. That is, assign all the round 1 queries to A1, assign all the round 2 queries to A2, and so on. So since A1 has budget B, all the round 1 queries, all the B round 1 queries are assigned to A1. A2 has budget B. All the round 2 queries are assigned to to advertiser A2. AI has budget B. All the round I queries are assigned to advertiser AI, and so on. And since the optimal algorithm assigns all the queries in round I to advertiser I, it is in fact able to assign each query to some advertiser. And so the revenue of the optimal algorithm is equal to the number of queries, and that is n times B. Now let's see what the balance algorithm does in this case. Now let's just imagine that these empty rectangles represent the unspent budget of each of the advertisers A1 through AN. And as we assign queries to the advertisers, we're going to color these rectangles. When the round 1 queries come in, now it's easy to it's easy to see that the balance algorithm is going to assign an equal number of round 1 queries to each advertiser A1 through AN. Now, since there are actually B round 1 queries, this means that each advertiser is allocated B by n of the round 1 queries. And I've shown that with this blue coloring on the slide here. Now, when the round 2 queries come in, the round 2 queries, the bidders are advertisers A2 through AN. A1 doesn't bid for the round 2 queries. And once again, the balance algorithm will assign an equal number of the round 2 queries to each of the eligible advertisers A2 through AN. Now, the number of eligible advertisers in this case is not n, but n minus 1. And so the balance algorithm will end up assigning B by n minus 1 round 2 queries to each of the advertisers A2 through AN. Now, similarly, when the round 3 queries come in, the eligible advertisers are A3 through AN, and there are n minus 2 of them. And so the balance algorithm will end up assigning B by n minus 2 queries to each of the advertisers A3 through AN. So in general, after k rounds, the allocation to advertiser k is given by the formula shown here. Sk, which is the allocation to advertiser k, is given by sum 1 through k b divided by n minus I plus 1. Okay? So the allocation to advertiser I is b by n plus b by n minus 1 plus b by n minus 2 and so on until b by n minus I plus 1. Now this process can continue for a while, but once after a few rounds, what's going to happen is that this allocation is going to exhaust the budget of the kth advertiser. At some point, Sk is going to exceed B, which is the total budget that's available to the kth advertiser. And at that point, we have exhausted the budget of not just the kth advertiser, but also all the advertisers, k plus 1, k plus 2, and so on through n, because all the advertisers k plus 1 through n have the same allocations. So if we can find the smallest k such that Sk is greater than or equal to B, then after k rounds, we've exhausted the budgets of all the advertisers, k plus 1 through n, and so we cannot assign any queries to any advertiser beyond that point. So our goal is to find the smallest k such that sk is greater than b. Now let's just look at this simple graphic that shows the allocations to the different advertisers. The allocation to the first advertiser, S1, is just b by n. The allocation to the second advertiser, which is S2, is b by n plus b by n minus 1. The allocation to the third advertiser is the sum of the first three terms and so on. The allocation to the kth advertiser is the sum of the first or the last k terms in the series, b divided by n minus k minus 1 all the way to b by n. And we want to find the smallest k such that the sum of this series is greater than or equal to b. Now what we're going to do to simplify the problem is that we're going to divide by b throughout. And that's equivalent to saying that the allocation to the first advertiser is 1 by n, the allocation to the second advertiser is 1 by n minus 1, and so on. And what we're interested in doing is that we're interested in finding the radix n such that the sum of the first k terms is greater than or equal to 1. So we want to find the smallest k such that 1 by n plus 1 by n minus 1 and so on through 1 by n minus k minus 1 is greater than or equal to 1. Now there's a very famous result due to Euler that says that for a really large n, the series 1 plus a half plus 1/3 and so on sums to ln n, the natural logarithm of n. This is true to a small additive constant, which we'll ignore. Okay. Now, what we've said is that we want to find the smallest k such that the sum of the last k terms of the series is equal to 1. If the sum of the last k terms of the series is 1, then the sum of the first n minus k terms of the series must be equal to ln n minus 1, since the sum of the whole series is equal to ln n. However, if we just look at the first n minus k terms of the series, they are 1 plus half and so on through 1 by n minus k. And using Euler's result once again, the sum of these terms can also be written as ln of n minus k. Okay. So there's two ways to write the sum of the first n minus k terms of the series as ln n minus k and as ln n minus 1. And so it must be the case that ln n minus 1 is equal to ln of n minus k. And when I solve that, I can solve that for k, and that gives me n divided by n minus k is equal to e, or k is equal to n times 1 minus 1 over e. So we've in fact found the k such that after k rounds, we've exhausted the budgets of all advertisers ak through an, and therefore we cannot assign any queries to any advertiser. So after the first k rounds, and k is n times 1 minus 1 by e, we cannot allocate any query to any advertiser. And so the allocation or the assignment or the revenue from the balance algorithm is given by b times n times 1 minus 1 by e, since in each round we have b queries. Now we've also shown that the revenue of the optimal algorithm is n times b. And therefore, the competitive ratio of the balance algorithm is just a ratio of the revenues of the balance algorithm to that of the optimal algorithm, and that's 1 minus 1 over e. So what we've shown here is an example of a scenario where the balance algorithm has a competitive ratio of 1 minus 1 over e. The actual proof that the balance algorithm has this competitive ratio and can do no worse than 1 minus 1 by e is outside the scope of this lecture. And I encourage you to read the actual paper for that proof. Now we've looked at a very simplified version of the AdWords problem, where all advertisers had the same budget B. And all ads had the equal expected revenue 1. Now, in the general version of the problem, this is not the case. In the general version of the problem, each advertiser has a different budget, and all the bids, each advertiser has a different bid for each ad, and each ad has a different expected click-through rate, yielding a different expected revenue. Now, in the general setting like this, the balance algorithm, as I've described so far, can actually be quite terrible. Let's look at an example. Suppose there is a query queue, and there are two advertisers, A1 and A2. And let's say A1's bid is 1, and let's say this is also the expected revenue, and A1's budget is $110. A2's bid is 10, and let's say this is also the expected revenue, and the A2's budget is $100. Now, let's say we see 10 instances of the query queue. When the first instance of the query queue comes in, we'll notice that A1 and A2 are both eligible advertisers, but we'll notice that A1's balance is much larger than A2 because A1's budget is 110 and A2's budget is 100, and so we'll end up assigning the query to advertiser A1. When the second query comes in, A1's balance is going to be 109, A2's is going to be 100, so the second query is going to go to A1 as well, and so on. So in fact, we will assign all the first 10 instances of the query queue to advertiser A1. And therefore, the revenue of the balance algorithm in this case is going to be $10. The optimal algorithm, as is obvious in this case, will assign all the instances of query queue to advertiser A2 and will earn $100. And therefore, the competitive ratio in this case is 10 divided by 100, which is 1 over 10, which is quite terrible. So it turns out that we can fix the balance algorithm to deal with the fact that advertisers have different budgets and different bids. And this is what's called the generalized balance algorithm. Suppose for query Q and bidder I, the corresponding bid is Xi, and the budget of advertiser I is Bi. Okay. And let's say the amount spent so far by the advertiser is Mi. Now the fraction of the advertiser's budget left over, which we'll call Fi, is 1 divided by Mi over Bi. Remember, Mi in this case is the amount that's been spent so far by the advertiser. Bi is the advertiser I's total budget, and therefore 1 minus Mi by Bi, which is given by Fi, is the fraction of advertiser's I that's left over to be spent. Now we're going to define this new term called psi I of Q. And psi I of Q is given by this expression Xi times 1 minus e raised to negative Fi. Okay. And what we're going to do is when a query Q comes in, we're going to take each eligible advertiser I, and we're going to compute this function psi I of Q, which is the product of the bid Xi and 1 minus e raised to negative Fi. And once we compute that, we're going to allocate the query Q to the bidder I with the largest value of psi I of Q. Now, I leave it as an exercise to you to show to yourself that in the case where all the bids are equal, all the Xi's are equal to 1, and all the budgets are equal, that is, all the budgets Bi are actually equal to a single budget B, allocating queries using generalized balance with the largest value of psi I of Q is equivalent to allocating queries to the advertiser with the largest unspent balance. Now, the generalized balance algorithm works in the general setting when the bids and the budgets of each advertiser are different, and in fact it achieves the same competitive ratio 1 minus 1 over e that the balance algorithm achieves in the simpler setting. So in this lecture, we've looked at an algorithm called the balance algorithm and the generalized version of it called the generalized balance algorithm that deals with the adverse problem in the situation with limited budgets and offers a better competitive ratio than the greedy algorithm. Thank you.